Hi, in this video we're going to look at variable acceleration, and in the next few videos you're going to be looking at these objectives here. So you should have heard of displacement, velocity and acceleration before in previous chapters, but now we're going to see how they can be given as functions of time. We're going to be using calculus, so differentiation and integration to solve kinematic problems, and we'll see where problems involving maxima and minima come into play, and also how we can use calculus to derive constant acceleration formula, in other words, SUVAT. So just a recap of velocity time graphs and what we've seen previously. We've seen constant acceleration before, so velocity time graphs that look like that potentially, or like that, and this is where the acceleration is constant. Now it will be different at the three various points on the velocity time graph, but it remains constant at those parts. So positive acceleration of the first part, acceleration of 0 on the horizontal line, and then on the third part a negative acceleration or deceleration as we think about what the velocity is at those stages as well. Just a reminder that velocity time graphs like this could go under the t-axis, so the horizontal axis here, but that would mean you've got a negative velocity and the particle or body is travelling in the opposite direction to what is positive. A couple of other things that we've seen before, in that in order to find out the acceleration at these parts of the graph, we would find the gradient of the graph at that particular point. So I could find the gradient of this line, the change in velocity with respect to time, okay, and I could do the same for the other parts. That's why I'm getting no acceleration here, because the gradient of a horizontal line is 0. I could work out the distance or displacement underneath the graph, or the total distance travelled or the displacement, by doing the area underneath the graph. So in this case it will be the area of a trapezium that I could use, or split it up into rectangle and two triangles. Now, we are actually going to be looking at something called variable acceleration. So we're not going to have straight lines anymore. We're going to be seeing some velocity time graphs, maybe like this. That's supposed to be a quadratic, or something like this. Something like a cubic. Sorry, that's as good as I can draw it. But we'll only be interested in when time is positive. So these parts here we'll be ignoring, and we'll just be looking at specific function when time is positive. So just to summarise, this particular example here is what we've seen in constant acceleration chapter, and this is constant acceleration, and in this case the velocity is increasing at a constant rate. These are the two that we're going to be seeing in this chapter, and the first one is increasing acceleration, so the velocity is increasing at a faster and faster rate, and then we've got decreasing acceleration, so the velocity is still increasing but at a gradually slowing rate. And if acceleration of a moving particle is variable, it changes with time and can be expressed as a function of time. So that's the same for velocity and displacement. They can be expressed as functions of time. So just to give you an idea, these are some of the equations that you're going to be seeing, and they're in terms of t. S represents displacement or distance most of the time. V is for velocity, and you could have a similar equation linking to acceleration. So we're going to see something of this form now. So a velocity time graph where we've got a curved part rather than a straight line part. So if I look at the first question, it says, if the acceleration is the rate of change of the velocity, how can we denote this using algebra? Well, I've just said that how we found the acceleration of a velocity time graph is by finding the gradient at a particular point. Now, we could find the gradient function of this curve by doing dv by dt, so differentiating the velocity with respect to time. So as the velocity is changing with respect to time. And that would be then the acceleration at different points. So the acceleration will be changing all along this curve because the gradient is changing all along this curve. That's why we've got variable acceleration now. So if I wanted to find the acceleration at time is 8 seconds, I would substitute t is 8 seconds into the derivative. How can we calculate the displacement? Well, in the previous slide, I was saying that the displacement, or the distance travelled, is the area underneath the graph. And in this case, it will be the area underneath the curve, so the whole of this bit. And we'll be interested in the area between two limits. So in this case, it could be t is 0 and t is 8. And how we would do that would be to integrate. So we would integrate v with respect to t. So just to summarise, we can differentiate to find the velocity, the acceleration. So if we're given displacement, we can differentiate the displacement to get the velocity, because the velocity is the rate of change of displacement. And then we could differentiate the velocity to get acceleration, because acceleration is the rate of change of velocity. You could also go straight from displacement to acceleration by doing the second derivative, so differentiating twice. The integration side, we could do the reverse. So if you've got acceleration, you could integrate it to get velocity. If you've got velocity, you can integrate it to get displacement. So you're going to see how calculus is required in these variable acceleration questions to help us solve problems. First, we're going to look at the functions of time aspect of the chapter, so no calculus just yet. If I read the example, it says a body in a straight line such that its displacement s meters from a point O at time t seconds is given by this, and we've got a restriction here, t has to be greater than 0. And it says find s, the displacement, when t is 2. So all I'm doing for part A is just a substitution. So when t is 2, s is going to be that. So I'll get 16 minus 6, which is 10, and I'll put meters there. So the displacement is 10 meters when time is 2. Now I've actually included the function just to visualize what's happening. This is the cubic, 2t cubed minus 3t. I've done it on Desmos, and I've actually put the axes for s and t. And because t is greater than 0, well, think about it, we can't have a negative time. We can have t equals 0, but we can't have t is less than 0. So I'm actually only interested in the part of the graph that I've dashed. The rest I'm going to ignore. So I'm only looking at what's happening in the graph after t is greater than 0, essentially. So this body is starting from a point O, and we're wanting to know in B the time taken for the particle to return to O. Well, here at time equals 0, it is at O because the displacement is 0. Now it travels away from the starting point, and then it returns back to the starting point when s is 0 again there. So I want to know what that time is, and it looks a little bit after 1. So what I'm going to do is I'm going to say, well, the displacement is going to be 0 if it's returned back to its starting point, and I will set this equal to 0, factor out t, solve, I'll square root. Now I've got 3 potential solutions for t, but it wants the time taken, not the times taken, the time taken. So this is where we can use a restriction. T has to be greater than 0, therefore it can't be 0, but 0 would make sense because that's at the start. Not interested at the start, we're interested in when it returns back to its starting point after leaving. So it's going to be the positive version of root 3/2. And in decimals, that is 1.22 seconds, rounded to 3 significant figures. And that makes a bit of sense from the diagram. You can see it's just after 1 second there. Right, the next example. A toy train travels along a straight track, leaving the start of the track at time t = 0. It then returns to the start of the track. The distance, s meters from the start of the track at time t seconds, is modelled by this, and we've got a restriction here. Now, all it's asking for in this question is to explain the restriction. So I think what's really helpful with some of these questions is to draw a sketch. You could have drawn a sketch of the last one. You can think about drawing the cubic, but the part of the cubic which is greater than 0. For this one, we're only interested in part of the cubic between 0 and 4 for t. So this is the cubic from Desmos, and as you can see, I'm only interested in this bit between 0 and 4. Now, why is there a restriction on that? You should be able to see from the graph why this part is only valid. You can use the sketch to explain the restriction, or you could do a substitution. You could substitute in values for 0 and 4, and then maybe think about what happens below 0 and above 4 and why that might not work for distance. So the first thing I think about is s is distance. If s is distance, s has to be greater than or equal to 0. It's not like displacement where you can have negative displacement. Distance is a magnitude, just a size, and it has to be positive. So that's why t cannot be greater than 4, because if you look at the graph goes into the negative s values after t is 4. So I'm going to say that if t is greater than 4, s is less than 0. I'm also going to say that t is time. You could have put this first. As t is time, t has to be greater than or equal to 0. So I can't go into the negative t values. Yes, I still get a positive displacement. It doesn't make sense in relation to this example in context. So I can't have negative time. So I might just clarify that if t is equal to 0, s is 0. The displacement at the start is 0 meters away. So therefore, that is the start. So I might just finish it off and say, therefore, we have this restriction. Okay, for the next example, you're going to see the greatest speed. So they're going to ask you what the greatest speed is within a range of values. And in these diagrams that we're going to look at together, it's going to be looking at from t is 0 to t is 4. So what is the greatest speed between those two values? Now, what students sometimes do is they sub in t is 0 and then they sub in t is 4. And actually, it doesn't mean that the greatest speed is at t is 0 or t is 4. It could be when t is 2, 3 or 1. So you've got to be careful here, and that's why a diagram could always be helpful. When we're thinking about greatest speed as well, speed is the magnitude of velocity. Again, it's a size, it needs to be positive. So I could have a positive or negative velocity, but I'm looking at which one is the largest, whether it's positive or negative, because I'll be doing the magnitude of that to get the speed. So in other words, think about the absolute value of the velocity. So if we look at the first one, I've got the greatest velocity being there. It's not when t is 0, it's not when t is 4, it could be when t is 2. So that is the greatest value for the velocity that I can find on the graph. So therefore that will be when the greatest speed is. This one, looking at the largest velocity I can find, I think whatever this value is will be the largest velocity. It's further away from the origin than this part is here. So this will be where the greatest speed, and that happens to be when t is 0. For this one, t is 0 is there, t is 4 is there. So I'm thinking here will be where the greatest speed is. That is going to be the largest velocity, but it will be negative. But again, because we're finding the greatest speed, that will be the value of it. If we look at this one, the largest velocity I can see there is probably going to be this point up here. It looks further away from 0 than that one does there. So the greatest speed will be there. And again, that is not 0 or 4 for t. It could be 1 for t, around there. This one, it looks like it's going to be where t is 0. That's the largest velocity and therefore the greatest speed. And then this one, have a look, that's where t is 0 here. But I think the largest velocity is actually going to be there. So that will be where the greatest speed is. So definitely helpful to have a diagram just to check you are getting the correct greatest speed. So the next example then, a body moves in a straight line such that its velocity v meters per second at time t seconds is given by this. For t is greater than or equal to 0. So we've got our restriction, makes sense for y, time is positive. Now we've got a few things to find, and if I need, I have got the graph that I've taken from Desmos again, so I can refer to that if needs be. Again, you can always sketch this graph. It's just a quadratic to sketch, and you should have those skills already in place. So part A, find the initial velocity. If you can remember back to when we were doing SUVAT, the initial velocity sometimes is represented by u, and that's just at the start. So at the start, the initial velocity is when t is 0. So I'm going to substitute in t is 0 into here. And you'll notice the first two terms are 0. So I'll get 24 meters per second. And that makes sense because if you were to sketch this quadratic, 24 is the y-intercept. So on the graph, that is 24 there for the velocity when time is 0. If I go to B, the values of t when the body is instantaneously at rest. We have seen this happen, this word, instantaneously at rest, before, but maybe we've not heard of that actual terminology. So if I've got a particle or a ball or whatever it is, and if I go back to vertical motion, when it was thrown up in the air, it would sort of follow this flight. And when we got to this point up here, this was where the ball or particle reached its maximum height. Now at that point, the ball or particle would be instantaneously at rest. So it would be at rest for a small period of time. And we were saying that's when the velocity is 0 at the greatest height. So it doesn't just stop and then it's completely finished. It stops for a moment of time and then is coming back down to either the ground or where it started from. So whenever it says instantaneously at rest, we refer to that as when v equals 0. So I'm going to make v equals 0 for this question. And in other words, I'm just going to be solving it. So I will divide by 2, factorise, and I'll get t is 6 or t is 2. Those both make sense because they're both greater than or equal to 0, and it does say the values of t, so I'm constantly checking whether I'm getting a value or values. So t is 2 or 6 seconds. Right, part C, the value of t when the velocity is 64 meters per second. So all I'm doing is another substitution when the velocity is 64, so putting that into the equation above. Rearranging and solving. I will divide by 2 again, and this should factorise quite nicely. Now I'm only going to get the one value, and it does say the value of t, and that's because I have to reject the negative value. T is greater than or equal to 0, so therefore t is 10 seconds. Final part, it says the greatest speed of the body in the interval. So this is what we were just looking at. It says in the interval 0 to 5 inclusive for t. So if I go to the graph, I've got it going up in 2, so 2, 4, 6. So actually 5 is going to be, if I do a dashed line, there. Okay, so that's 5. So between 0 and 5, which is the greatest speed, well, it looks to me like the greatest speed is actually the 24 meters per second when t is 0. So there's a few things, or a few ways you can do this. Using a graph, quick sketch, look at where you can find the greatest speed, or substituting values. But you're going to have to be careful because, as you have seen on the previous slide, it's not always the endpoints that produce the greatest speed. So I'll do a combination of the two. You could just say from the graph, it's 24 meters per second. I'm actually just going to do some substitutions as well. So when t is 0, v is 24. Do a little arrow. When now I'll do t is 4 because that would be the minimum point there. I can see that's not going to be, or not going to produce a greatest speed because it's not minus 10. It would have to be less than minus 24 in order to produce a larger, greater speed than the 24 up there. But I'm just showing that through substitution. You will get minus 8. That is the minimum point. And then I'm going to do t is 5 and v is going to be minus 6. So that point there is minus 6. And you could try 1, 2 and 3. I would definitely recommend that if you haven't got a diagram. It's quite quick to do on your calculator. If you remember, you can use the calculate mode. So type in the function and then press calc and change your x values for 0, 1 all the way to 5. It should be quite quick. From here, because I've got the diagram backed up with some substitutions, I can see that the greatest speed equals 24 meters per second. Okay, there is some practice. So exercise 11A, you can have a go at that.